Good day, ladies and gentlemen. I hope you are all well. Uh, Welcome back to the lesson. We are still back now with Newton's second law of motion, and today we'll be focusing now on when an object is on an inclined plane. And then, as you know, we'll first now take an example and see how now do we go about solving a problem where now an object is on an inclined plane. And then from there off, we'll start with now this simple uh, example, and then we'll go and look at a more complex example. So let's without any waste of time get down to this example of ours and see now how do we solve now problems of now objects on an inclined plane. And then it says the example: a 25 kg block is placed on a rough surface. That rough surface, ladies and gentlemen, it must tell you something. And I know you know that this rough surface implies to us that now the surface where the object is resting on, it is now a rough one that has a friction. And then it further goes on to say an inclined plane at 30 degrees to the horizontal. And then a constant force F acting parallel to the surface is applied on the block so that the block moves up to the incline. So they are telling me that this block is moving up in that direction at a constant velocity of 2 meters per second. Ladies and gentlemen, what the examiner is trying to tell me is that the block is not accelerating. The block is not accelerating. Why? Because it is moving with a constant velocity. And then we know that when we did motion in one dimension in grade 10, we said now when an object is moving at a constant velocity, its acceleration will now be equals to 0. And then the statement further says, refer to the diagram below. This is the diagram of the object that is now moving up the incline with a constant velocity. And then it says to us there, a constant frictional force of 18 newtons acts on the block. And then there is our diagram there, ladies and gentlemen. So the approach to this question, you all know the approach to every problem in Newton's second law of motion. Without me looking at these questions that I will answer later on, you know the approach, ladies and gentlemen. Ladies and gentlemen, the approach is that we must now draw a free body diagram. And we know that I will draw now two free body diagrams. Free body diagrams. But then I will start now with the free body diagram without components. And then I will then draw another free body diagram with components. Let's first now draw this free body diagram without components and try and understand where does these components of a free body diagram come from. So in order for us to draw a free body diagram, ladies and gentlemen, for an object that is on an inclined plane, I will follow these simple steps to say, there is my incline, then I will just use now my pencil to draw a dotted line like that, ladies and gentlemen. This dotted line here it now shows me my inclined surface there. And then we know that for us to draw a free body diagram, we must then have a dot there. That's when I will have my dot there. And then because the object is on the surface, it's on this surface, we will agree with me that we must have a normal force. And we know that a normal force, it's a force that acts perpendicular to the surface. So when I draw it here, ladies and gentlemen, I must draw it in such a way that this normal force, it is perpendicular to the surface. You'll agree with me that this is perpendicular to the surface there. And then we know that this object of ours has mass. And then if that object has mass, we know that the force there that must be acting downwards, it must now be the force of gravity. And the force of gravity will go like that. And then this will now be my Fg. And then Fg now goes downwards. We know gravitational force pulls objects now downwards. And then again, I will then have this force. And then we know that that force will act now in that direction there. And then this will now be force F. And then I was told by the examiner that there is now a rough surface, meaning there must be now a kinetic frictional force there. And the kinetic frictional force must oppose the motion. Then it must go downwards like that. And then this will now be Fk. And then this, ladies and gentlemen, this will now be my free body diagram without components. So the components that we are talking about here, ladies and gentlemen, the components that we are talking about, it's the component of the weight. We are going to have two components. Let me come this side and draw now this free body diagram. Free body diagram. A free body diagram with components. And I know that you'll agree with me that these components that we are talking about, it's the components of this force. And this force, we said this is the weight force or the gravitational force. So this gravitational force of ours, ladies and gentlemen, has two components. Which we call now the parallel component and the perpendicular component. Ladies and gentlemen, I will have my slope here. I said I will use now these dotted lines to indicate now my slope. And then I will have again my dot there. I will make it big there because I will have the components there. Still, I will still have now my normal force. And then when I have my normal force there, it says to me that I must also have this force applied there. And then here I still had now my Fk, which is my frictional force, which is Fk. And then when I want to draw the components of this, ladies and gentlemen, I'm going to have now the parallel component of Fg and also the perpendicular component of Fg. Now, the perpendicular component, ladies and gentlemen, it will then go in line 180 degrees with the normal force. but it will then go in opposite direction there. So this will now be my FG perpendicular, the perpendicular component of the gravitational force, or of the weight. Can you see that this FG perpendicular, it is perpendicular to the surface, hence we call it now the FG perpendicular. And then because this is a component, this component must have now another component which we talked about, that it is a FG parallel. And then, ladies and gentlemen, please, this is the gravitational force, and we know that gravitational force always acts downwards. So whether the object is moving up the incline or down the incline, my FG parallel will always now go downwards. My FG parallel will always now go downwards. This is the parallel component of what? Of the gravitational force, or the weight force there. So when you want to draw a free body diagram, either you draw this one without components, and we know the one with components, we will draw it for the examiner there. And the one with components, we will now draw it in order now to solve the calculation problem. And then it says to me, this gravitational force has two components: the parallel component, which always acts downwards, and the perpendicular component, which now is now acting at 180 with the normal force. I hope we got that, ladies and gentlemen. And it further says to me, my FG parallel will be equals to the FG sine of theta there. And then my FG perpendicular will now be equals to FG cos of theta there. Now we are saying these are the components of FG, or we'll say now the gravitational force. These are the components of the gravitational force. And ladies and gentlemen, these components, they do not change. FG parallel will always now be equals to FG sine of theta, and then FG perpendicular will always now be equals to FG cos of theta there, when now an object is on an inclined plane. And let's now try and find an analogy that we can use in order to remember these components. Remember, these components are not there in our formula sheet. So let's try and find an analogy that we will use here to say now, how do I remember this component? How can I remember this component in an exam? So whenever you are faced with a problem that is on the inclined plane, just now remember this keyword to say pass peg. But say, what does pass peg mean? Pass peg just says now, for the component that is parallel, I will then use sine theta there. And for perpendicular, I will then use the cos of theta. So this pass peg, ladies and gentlemen, comes in handy when I'm dealing now with objects on an inclined plane. Only for objects on an inclined plane. This is the analogy that I can use now in an exam to help me to remember to say that the parallel component, it is, I must use now sine of theta there. And then the perpendicular component, I must then use now the cos of theta there. And then with that being said, ladies and gentlemen, we can say now, let's go now to this problem of ours. Then the first question says, draw a free body diagram for the block. Here is the block, ladies and gentlemen. And remember, we said if the question is asked in an exam to draw a free body diagram, this is the free body diagram that I will be drawing for the examiner. And as you can see, it's 4 marks there. Then I'm also having now 4 forces there. 4 forces. To be on the safe side, ladies and gentlemen, draw a free body diagram without components. If the examiner wants now you to draw a free body diagram. Then the second question says to us, calculate the magnitude of the of force F. Now, for force F there, ladies and gentlemen, this will be number 1, and then this will now be number 2 there. For us to calculate this magnitude of the normal force there, you'll agree with me, we'll start by saying now F net is equals to MA. And then because I'm going to be involved in a calculation there, it says I must look at my free body diagram, the one with components, so that I can see all the forces there that are acting. Can you see here? We only now see that there is a frictional force, but unaware that there is also now a component of Fg there, and then the component of Fg which is acting on a parallel to the surface there, it is Fg parallel. So in total, I have now 3 forces that are acting parallel to the incline. These forces that are acting parallel to the incline are the ones that are going to cause the object to move up and the object to move down if the object is moving down. So we are saying, let me now choose my direction, and you'll agree with me that where the object is going, let's take that as positive, and then downwards will now be negative. Up the incline, positive. Down the incline, negative. And then you know that we'll then first start with the positives to say F plus negative Fg parallel plus negative Fk is equals to Ma. We know that, ladies and gentlemen. And then I can further say now F plus, can I break this Fg parallel? We know that Fg parallel is equals to negative Fg sine of theta there plus negative Fk is equals to Ma. But ladies and gentlemen, we said now this is the weight force, and we know that weight, or the gravitational force, Fg is equals to mass multiplied by gravity. So this now also now comes in handy there, to say now where I see Fg, let me substitute now the mass multiplied by the gravitational acceleration. So I will then say F plus negative mg sine of theta there plus negative fk is equals to ma. So this equation is the one that will then help me to find now the magnitude of f. So I will then say f minus, because a positive next to a negative, it gives me a negative there. Do I have the mass? Yes, ladies and gentlemen, I was given the mass. The mass was 25. So I'll say 25 into the gravitational acceleration. What is the gravitational acceleration? You'll agree with me that it is 9,8 multiplied by the sine of theta. Theta here, ladies and gentlemen, it is now the angle between between this incline here that the incline makes. It's the angle that the incline makes there. So the incline makes now an angle of 30. So I will then have here 30 sine of 30 minus, I was given the frictional force, to say the frictional force is 80 is equals to the mass. The mass is still 25. And then we agreed that this is moving at a constant velocity of 2 meters per second. Ladies and gentlemen, let's clarify this. We know that from grade 10, we know that acceleration is given by the change in velocity over the change in time. And we know that the change in velocity there will be Vf minus Vi, and then this will now be divided by the change in time. But it says to us the block is moving at a constant velocity. So it says to me, if it's moving at a constant velocity, the initial velocity will be equals to the final velocity, meaning that the final velocity will be 2 meters per second, and also the initial velocity will be 2 meters per second. And then we know that here 2 minus 2 will give us a 0 there. And then let's say now this object of mine took now from here to there, let's say now it took about 4 seconds. But then I will still have a 0 divided by 4. And then 0 divided by 4, you'll agree with me that that is a 0 there. So this now, for us to say acceleration is equals to 0, it comes now from this scenario there, that when an object is moving at a constant velocity, its initial velocity is equals to the final velocity. So ladies and gentlemen, here I will then substitute my 0 there, and then I will then take my calculator to say, let me work with this. And be careful when you substitute here, this is negative, so I will substitute that negative to say negative 25 into 9,8 sine of sine 30. Then this gives me how much? It gives me now minus 122,5 minus 80 is equals to this. Ladies and gentlemen, you will agree with me, it's going to give us a 0. So I will then say minus 80, and then this gives me a force minus 114,5 is equals to 0. So my force there will now be equals to, I'm going to transpose there, my force will now be equals to 140,5 newtons. but this is a force. It must have now a direction. And then if we want direction, they will say now up the incline. But here we just wanted now the magnitude, so we would have been totally correct if now we were just given that a 140,5 newtons. But if now they wanted the direction, we'll say now this will now move up the incline there, ladies and gentlemen. I hope you are happy with that. Then the examiner can even go further to say calculate the magnitude of the normal force. In this case, ladies and gentlemen, the examiner now wants the normal force. If the examiner wants the normal force, I will then go again to my free body diagram, the free body diagram with components. And then if I look there on my free body diagram, I can see that my normal force, because my normal force is in this direction, and we said that this object is not a moving in this direction, it only now moves in that direction. So what does that say? It says to me that the sum of these forces in this direction, they will then give me a 0 there, to say now the F net in that direction must be 0. So it then says to me my normal force plus they're in opposite direction. So this one is positive, this one is negative. So plus negative Fg perpendicular will then be equals to 0 there. So my normal force, ladies and gentlemen, let's squeeze it here. My normal force will then be equals to Fg perpendicular there, and we know that Fg perpendicular is equals to Fg cos of theta, and then we said Fg is equals to mg cos of theta there. So I can find the magnitude of the normal force to say mass it's 25, then gravity it's 9,8, cos of the angle there, it's still the angle that the angle of the incline, which is a theta. So here it will now be theta, and then when I substitute that into my calculator, I will then get 25 9,8 multiplied by the cos of theta there. So the magnitude of the normal force there will then be 221, 2 decimal place, 8 newtons. So that will now be the magnitude of the normal force there. So ladies and gentlemen, we must be aware of this, that when I have an incline plane, my normal force will then be equals to the perpendicular component of the gravitational force. So with that simple example, ladies and gentlemen, I hope now you were able to learn something here. So we said now we'll then look at a more complex problem. A more complex problem just says to me that I will now have two objects, one connected to the other with a strain there. So we'll look at that, ladies and gentlemen. I hope you enjoyed the lesson. Thank you very much.